Imagine you are a passenger of a self-driving car that sees a stop sign but interprets it as a speed limit one and causes an accident because someone very subtly tampered with the sign itself. If you believe it is only a hypothetical situation, have you ever seen this experiment? Or have you ever seen this diagram? In this video, I'm going to talk about how the deep learning models can be fooled by adversarial examples. Many supervised learning problems are solved after representing them as optimization problems using loss or cost functions in terms of model parameters. But what if we maximize loss and the corresponding error by optimizing over inputs instead? In the deep learning case, the core idea is learning via backpropagation. The models should be differentiable in order to check the gradients with respect to the parameters, so we could update those and improve performance of the model. But again, what if we use the gradients to poison the inputs we feed into the model instead? This sudden downfall is known as a white box attack, which means the precise model structure, including its weights and gradients, is known to an adversary. In contrast, the black box attacks are performed when the adversary or attacker can only interact with inputs and outputs of an unknown model. In 2014, a group of researchers showed that, contrary to our previous beliefs, the deep learning is indeed highly vulnerable to optimization over inputs. However, their approach turned out to be computationally expensive, so in 2015, 3 researchers from Google used the popular gradient step not to correct the model parameters, but to craft the fallen input images. This single-step method was called fast gradient sign method, and we are going to take a closer look at how it works. Adversarial attacks are usually supposed to be imperceptible for humans. For instance, in images, an adversary might want to make sure that each individual pixel is modified only so much, just within small bounds. That is why in pixel space, the modification vector, let us call it eta, is bound by a small L-infinity epsilon ball that you see in the graph. For changes that small, local linearity assumption holds. That is, the loss function shall behave almost linearly in the proximity of the original image. Therefore, we can use the loss gradient with respect to input image to see how much loss is gained after the modification. Dot product between the gradient and eta yields a precise estimation. So, now we need to make a single step to maximize the loss gain, and the loss grows fastest in the gradient direction. Why don't we just clamp gradient onto the epsilon ball? Indeed, that would make sense if the ball was Euclidean one. However, for L-infinity constraint, the things are different. We can illustrate that the optimal solution is the sign of gradient scaled by epsilon. Feel free to pause the video and think of it. You can also imagine this optimization element by element. Try assigning elements of eta, they should stay in minus epsilon to plus epsilon interval, one by one to maximize the dot product. You should end up with sign of gradient scaled by epsilon as well. The described gradient sign step is optimal under the assumption of local linearity. On a bigger scale though, the assumption does not hold. Or does it? Surprisingly enough, even after going out of the epsilon ball, the crafted adversarial inputs remain highly effective, just not optimal anymore, which sometimes is a small price to pay for how quick the method is. However, there are options to extend the attack beyond a single gradient step. To do so, we firstly decrease the step size to alpha, then repeat the FGSM step multiple times, and project back to the epsilon ball whenever we go too far. This way, the input stays within the epsilon bounds, but the iterative nature of the method allows to create strong adversarial examples. The method was introduced by MIT researchers who labeled it a universal first-order adversary. That is, the strongest attack utilizing only the local gradients of the model. This way, the increased computational cost pays off, because the user obtains stronger attacks. The methods I have just described, namely FGSM and PGD, are foundational, but the whole thing doesn't stop there. The core idea of using gradients to somehow manipulate the inputs is extended in many ways, including, but not limited to, the following. For instance, you can add the momentum term to obtain momentum iterative method, or you can search for the closest misclassification instead of the most powerful one, and you're going to have Karolina-Wagner attack. The list can be continued, since adversarial machine learning is mostly an arms race. Both attackers and defenders try to come up with something new every time, which means that the sophistication grows, and that hypothetical situation you heard of in the beginning of the video is not that hypothetical after all. If you got interested in the adversarial attacks even for a bit, I suggest you check out the repository I left in the video description. You may definitely find something interesting here. Thank you for your attention.